So I first want to talk about privacy pass, because I really like it, because I think it's a very, let's say, kind of fun and elegant solution which uses zero knowledge proofs in a part of their work, like smaller part, let's say, and I really think it's quite nice. Also because other people as well developed something on top of it. So Privacy Pass is a work by Alex Davidson, Ian Goldberg, Nick Sullivan, George Tankersley, and Filippo Lazzorda, which was published in 2018 at PATS. Like a paper was published, but they did work on it 2 years prior already. So actually it was developed when some part of the group was at Cloudflare, and Cloudflare needs to prevent attacks. They get like requests, and there's IP addresses which send something bad, and they want to not communicate with those IP addresses. And what they do is they use IP reputation to see if that IP address might be malicious or might send malicious things. So yeah, we all know how to know if your IP address is good or bad. We get something like this, a CAPTCHA. So yeah, as I said, we would use CAPTCHAs, and everybody who's interested in privacy knows how annoying it is to be on tour and have to solve like tons of CAPTCHAs, because everything you want to Google is, not like Google is not sure, if you're good or bad. Anyways, the idea on what like Privacy Pass is based, or what Privacy Pass wants to do actually, is for you to get a token. So not to always solve again the CAPTCHAs, being like, okay, like I did show that I'm a human like 10 times in a row in the same session, but to do it once and get somehow a token or some kind of pass, privacy pass, to then be allowed to not solve the CAPTCHAs anymore, like all the time. So the idea is to have this token, but on the other hand, obviously, like we don't want to have like, this is why we have to like solve CAPTCHAs all the time. We cannot just like have cookies which normally follow us around, right? So we want to have somehow a blind private token something. So the idea is based on Ecash, which was based on a paper from 1983. And the idea is there also to have like somehow the token, money token, like floating around. And you use blind signatures for that. And so the idea was also for Privacy Pass to use kind of that idea of sending a blind token and like putting a blind signature on top, and then you can use that as a pass. And that's also great because like you cannot link if like when I issued that my pass, you cannot link that to the redemption. So the part of the group at Real Crypto 2016, we're starting on that idea and we're thinking about how to actually develop it and what to do. And they actually just wanted to adopt that idea for this problem of solving CAPTCHAs and having a privacy pass. And they tried, and they did find a solution, but the problem was that this was not very efficient. So just to give you an overview of how like this would look like, so we have an elf, which is the user, and we have a fairy, which is the server. Don't ask me why, I thought it's nice. So we have the elf who has a token, generates a token, he blinds it, and sends this blinded token to the server. Then that server, the fairy in our case, does a like digital signature, has a private key, mints a private key, and sends back this a blind signature. And so neither the fairy, the fairy doesn't know, cannot link like this issue tokens back to the tokens when somebody wants to redeem it. And this is what happens when we want to redeem it. We have the elf who sends token and his signature to the fairy and gets back like some values, some things. So this is basically the top idea, let's say, or how that is supposed to be working, high-level idea. But as I said, this was all like the idea of Ecash was based on, like, it was from 1983, so it was based on RSA and not very efficient, kind of slow. And so the part of the team asked for help. And then Bonnet actually mentioned elliptic curve OPRFs, which are great. So yeah, so it's that are oblivious pseudorandom functions based on elliptic curves. And George Tankersley actually like developed a batched version with redemption where you can batch a lot of them together. And just to understand kind of the difference, like the idea is that like in Ecash, you obviously want to have like a cache token, let's say, how we have like real cash, where it's absolutely clear, it's publicly verifiable. This $20 are actually, like everybody here will say, yes, these are $20. But with verifiable oblivious pseudorandom functions, it's actually quite different, because we want to only be able to verify them by this issuer in this redemption session. So only in this case, like, yeah, you'll pretend you live in a like very small place and you have a very unstable government, and then only then your dollars are stable and you can actually redeem them, just to have an idea. And this is also something we want, because we want in a privacy pass to not be able to do that over the whole time. Yeah, and so this is where, like, this sounds all great, perfect. As I said, I want to give you the high-level ideas, or like places where to look at, where you then can look at the code or can look at the documents and understand the concept already, and then you can see, okay, but where do they use ZKPs? Where can I use the cryptography? So actually, what they do is they use in this construction of the elliptic curve OPRFs. Sorry, there's a beep too much, I think. They use actually discrete log equivalence proofs where they need to, like, it's a very like nothing too crazy. It's really just understanding if those are equivalent to discrete logs. So that's actually quite nice, because it's a starting point to, like, if you want to dive in and see how an action application is using zero-knowledge proofs, we see all these great, cool applications having very interesting constructions. And here, this is, for me, I thought it's quite elegant to do it in this way. So again, I wanted to, like, this was before that, the Ecash explanation. So here, basically the same thing. We are also sending the captcha. And this is actually how it works. I just put it on one slide, which is, I think, not best practice. So sorry for that. Actually, it's quite nice, and you can have a look at protocol documents where they explain actually very nicely, in my opinion, how you can like naively start and then go in 7 steps to this, and understand why you cannot naively just like send, for example, a token and somehow blind it, and why you need to take extra steps. So, for example, I'm just going to like, we have here the blinding factors. Also, what we use are, we make sure this is unlinkable, so we do not just like generate some points, but we have an integer which we hash to a group element and then blind that and send that. What we also do is we have here the zero-knowledge proof that I was talking about before, which actually, like, this is a long equation, but this is the same element as this one. So we do just show that this is a discrete log, like this has the same discrete log property. So yeah, and I thought it's actually quite nice. So this is just like a high-level idea of how this works. But as you see, what we do is we generate here some kind of tokenish style, blind that here with the blinding factors, send that to the issuer, and the issuer signs it and turns a proof. And then when we want to redeem, what we do is we send, because like we can do that in a batch. So what we do now, we don't have to redeem all of them at once, because obviously we don't want to do that. We want to like get, like once we did a capture, we want to get like a lot of tokens, let's say, and then we want to redeem each of those and using an HMAC. So this is the idea, and I hope you got an intuition of how that works, or like how that this is something you could look at if you want to like understand first like why you would need to even introduce the zero knowledge proof firsthand, because this is, I think, a great project to look at for that. Also, there's an extension for Firefox and Chrome as well, and yeah, there's like some problems like regarding double spending, but you can do time charting. I'm not sure how like far that idea is going, but this idea actually could also be used for example, anonymous session assumptions for TLS, or referral code mechanisms where you have a discount code and you then want to like send it further. And also just for like single bit zero knowledge proofs. And so as you see, like there's this idea has a lot of cool, nice implications. This idea of just using a zero knowledge proof just for like seeing if two discrete logs are equal. And there was somebody else who used the same idea. As I said, there's like some ideas, but there's also like a real tangible idea which I found, which I thought is quite nice. It's called private storage, which is a project done by Least Authority and Private Internet Access, who is they're a private VPN, and Least Authority does storage solutions, private storage solutions, and security audits, and a lot of other things. And they announced recently private storage. Sorry, that I'll just show it. This one does not belong here, this line. And so private storage is, as it sounds, a private storage solution, cloud storage solution, based on Tahoe loves. And the problem was that they needed a more robust access control mechanism, because the idea is that when you pay for a storage solution, and you at some point, you can use the storage solution, right? But at some point you might not pay anymore. But if you want to have a real private storage solution, you also don't want, there might be use case where you don't want the, let's say, issuer or the people who actually give you that private storage solution to know who you are and to link you and to actually track what's happening, and if you specifically, how long you were in and all of this information. And this is something Least Authority and Private Internet Access are very passionate about, giving the most of privacy to people, most of freedom in that way. So the problem was that traditional accounting methods didn't work, because they couldn't track who paid and who would be able to use their private storage solution actually. And they used zero knowledge access passes, kind of the same idea as privacy passes, to track from each session to each session if this user already paid and for how long, and if they can use actually the private cloud storage, which is then based on Tahoe loves. But just the idea is, I think, quite nice, because it shows that something like privacy pass, which when I first heard about it, I was like, okay, that's valid, valid problem we have to solve, but also it's quite small, maybe. It actually shows that ideas like this can be used in a lot of different contexts. So I hope you get that idea. So we have seen one or two exotic animals, and I hope you find more with this knowledge now. And so this was the first, so this is the press blog entry. So this was the first kind of part where I wanted to show you something where I've seen like more potential in. And the second part I want to show you is actually something I worked on as well, on auditing technology. This is a joint work with Jan Kamenisch, Manu Drivers, and Maria Dubovitskaya. And all of the three are now with Dfinity. This work was, though, done while we were at IBM. So the problem is when auditing, so this is a very different problem, so I hope you can switch off your brains and get back to another problem. So the problem is now we don't have a privacy pass anymore. The problem now is we have two users, or a lot of users, but let's take two. And one of them, the rockstar, emoji on the left, wants to show that some data that he did is actually like consistent, and for some identifier he has some data. And he doesn't want, like we don't want, and he doesn't want, to show that for this data identifier, he might have two paths kind of following. That's what I tried to paint there. So for one, for example, for April 2018, something happening there, he wants to show, okay, I really just have one set of data for that, and not I have like 2 different bank transfer sets. And we have auditors in our same, let's say in the same world, living in the same world, who actually want to see that he really has just one audit log. And this is the idea of audit logs. And you can use that for financial data, like medical data, and any other data where you have a data identifier and some data. Yeah, oops. Okay, yeah, so this is how it would look like. For example, as I said, financial statements, we have some data identifier and some data details. And the main idea is to, like this was the goal, to put this somewhere. We're going, like we were using a blockchain because of the unfalsifiable, yeah, kind of property, yeah. And anyway, so we were, you want to have like some data identifier, data details, you want to have a timestamp, and being able to secure this and this information to be private. Obviously, I don't want to open up all of this information to everybody, but just to the auditor in the room. So this is the basic idea. And now the question was, after we understood our problem, is how to actually construct such a cryptographic protocol. And I want to like shortly introduce you to something that I'm like passionate about, and some cryptographers too, and some not, but that's I think always the case. So it's always good to have for such a solution, which is very practical, a modular cryptographic approach. So the idea behind that is that if you design a cryptographic protocol, you don't design it once and then you prove some properties in that protocol, but what you do is you actually can use some other functionalities of cryptography, and you can introduce them, and you don't have to necessarily, with those small functionalities you use, you don't have to show specific things about those ones. And also, your protocol later can be embedded in different other protocols. So if you're interested in cryptographic design, this is one of the, let's say, cryptographic design ideas or proof ideas also later. And this is called universal composability, because you can universally compose things together. And just for you to understand how I'm going to present a protocol now, like later, like now to you, just to have an idea how you would prove that a protocol is actually secure. What you do is you actually have an ideal world on the left in green, where we have like, it's the ideal world. It's heaven, nobody's bad, everybody's great. And we have a simulator who simulates all the bad guys. So he's simulating all the bad guys, and we have an ideal functionality. It's working perfectly, and this ideal functionality is passing the data exactly like we want it to pass. So this is the ideal world. We know it doesn't exist. So we know that there's the real world, where actually we have a protocol, and we have people communicating, and an adversary, and always different ones, obviously. And we have the environment, which looks at this world from like it's the same environment. That's why I try to make it gray in both worlds. And the environment now, what we want to show is that if you're sitting in an environment and you're communicating, either you're communicating with something. The idea is to show that you're not able to tell if you're in the ideal world or if you're in the real world. That's the basic idea. Because if you can do that, you know that like, if you are not sure and the adversary doesn't learn anything more than we defined in the ideal world, we know that no other data can be leaked to the adversary. I hope the idea somehow got through. So the idea is we want to, the environment should not learn anything, should not understand in which world it is. It should be indistinguishable. And all of like the ideal functionalities, the users who are communicating are all interactive Turing machines, just for like, yeah, if you're interested in how theoretically that looks like, let me know. But yeah, so this is what we want to do. I want to show that for any real world adversary, there exists an ideal world simulator who can kind of capture that, and then this is indistinguishable. Okay, so just for you to understand, because what I want to do now is actually show you how we defined security in this model, and how we actually then build a protocol, and just for you to like get the idea. What we wanted to have first before actually building the security model, the ideal functionality in the ideal world, as I just tried to explain, is wanted to have several security guarantees. 4 were related to transaction itself, the transaction being the data set, like data identifier, data details, and 1 was on the record integrity, and 2 were on the auditing process. So obviously we wanted to have transaction privacy. This is why we started the whole thing, because otherwise you can just put everything on blockchain in clear text. So we want to have some privacy. Also, we want to also have transaction authentication and know what's happening there. Also timestamping, because we don't want to later on like put some data, let's say, on our bulletin board and not be sure if it was already there in the moment when we actually said it would. And also we want to have transaction uniqueness. This is what I was saying about the 2 paths. Then also record integrity, in the sense of when we record something, it should stay. Audit authorization, so not anybody can audit the things that we need to, and auditing correctness. So how our security model looked like, this is the first part, is what we actually did. This is, you can think of this as an interactive Turing machine, and we have like we have one user and another user. Just to mention, as I said, we can have n users, all of them can be audited, all of them can audit. But here in this case, I was trying to make the small emojis. The cat is the bad guy and is the adversary here. So what is happening is that this is the recording part. And what we want to do, what we want to have is, this is the ideal world, the user who wants to be audited, the auditee, should record something with session ID, something with record ID, and his data ID and his data. And what should happen in the end is that the auditor, okay, sorry, here should be the auditee. So please think of a rock star hiding under this hat. So the user I should also see that his recording got done. So you can just like skip those, skip the auditor. He's not or she's not involved here. And what we want to do is then, what we do actually in ideal functionality is, since this goes over an insecure network, we have to tell, like there is some communication with the bad guy, with the adversary. And also we communicate, as I said, we're actually using here the generalized universal composability framework. That's why we have a global functionality here, which we use as a reference clock. So what we do is we actually look, does that exist already? If so, we just cancel. Does the record ID exist already? If so, we cancel. We get a time and we have to put this temporary away. And then we have to let the adversary know this is the ideal world. That's why the ideal functionality is working ideally, and we have to model kind of the real world. We have to like leak, this is a leakage function, that something happened. That we can like let, like in a network, the adversary would know who that is and what session it is, but not necessarily data ID. And when the adversary does not cut off our network, he will give us kind of like an okay. Otherwise, like ideal functionality doesn't do anything. We actually record that. We actually search for it and record it to a transaction list, and delete the temporary edit and say, okay, done. So this is kind of just for you to understand idealization. We also do that for the audit. Here, in this case, we actually do need that auditor here. So yeah, now that detective is actually a detective. So what is happening is that we again send as an auditee to whom we want to actually open up our data. We again look if this exists, get the data, check. We do some checks to make sure that, like in the ideal world, no adversary should like communicate, should be able to like communicate, and put that temporary away, let the adversary know. And when he says okay, we actually get that from the temporary list, put that in a list from the audits and send that back. So this is kind of just for you to understand how like such ideal functionalities would look like. So yeah. What we then do, the real world protocol, is looking like this. Okay, it's actually a LaTeX like file with some other things, but this is the idea of it. So I would be happy to talk about it later. I just wanted to give you an intuition. First of all, the blocks here, as I said, we're using universal composability. So what we have here is different building blocks, and this is very useful. I'll explain shortly why, because we now build a protocol. So this is the real protocol as a cryptographic designer or cryptographic, we build a cryptographic protocol. So normally we really have to, like here, we use two hash functions, and what we can use in this case is two different random oracles. And also, for example, we use here a blockchain. We modeled this in an ideal functionality as blockchain. So when we design the protocol later, it's easier, much easier to design this protocol, which is quite complex, than actually doing it through reductions. So on a game-based approach. So we have again the same, we have again an auditee and an auditor. Both of them have the same set of like a secret key and a public key, because it could also be the other way around. For that, we will need complement reference string and also certification authority to actually register those keys. But we don't need to show specific things about the certification authority, because we can actually just use the building block in universal composability. So this is the block here. And what we do then is, this is the record part. So what actually happens is actually quite easy. We have the data ID. We hash the data ID and put it to the power of the secret key. Yeah, so we do hide it a little bit. And then we get like some kind of tag. The same thing we do with the data. And what we attach to that is, again, the hash of the data ID, but with the other hash function. So two hash functions. So this is the data tag. This is the protocol that we would be using. And the tag and the data tag are going then onto our bulletin board, which is time-stamped. So we use a timestamp bulletin board with a recording ID. So this is the idea. And for auditing, what we then do is we then have to send to the auditor here, sorry, and we send four parts of the data to the auditor. A tag, then the second part, which we attached, a proof that that all of those are actually, this is where the zero-knowledge proofs comes in. We use a NISIC here. Later in instantiation, we just used Schnorr with a Viertermeer transform. But this is why I wanted to show you that if you design cryptographic protocols, you have to do it correctly, and you have to think about it, what you do. But it's really a good intuition to use your knowledge proofs where you want to actually show that something correctly happened, as we want to do here. Mm-hmm.
Why is the same the data type?
Sorry, the same H hat in?
H hat is used inside the
here
and also outside.
Yes.
There are two different places that should never be confused.
Yes, but actually we use actually two cryptographic, we use those two hash functions, and we actually, this is the idea, we hash the data ID once for one hash function, once for the second, and then hash it again with the data.
No, I'm asking why that H hat inside is the same as the H hat outside of the data type, rather than using three different hash functions. Maybe we
can take that offline, okay. Because okay, yeah, but let's discuss it. It's quite interesting for me. Good question for me as well. Or might be. So yeah, we use zero-knowledge proof here, and we attach the data. What we in the protocol design assume here is a secure messaging transaction. Yeah. So we use here secure messaging, and then the auditor can actually recompute this data tag here and check on the timestamp bulletin board. So this is the basic idea, and I'd be happy to take any questions about the protocol. And so we were implementing this on Hyperledger Fabric. And we did that for the client SDK actually in Java. So that was quite slow, but they needed it in Java, so okay. We used AMCL, and which is very useful if any of you want to use it. As I said, we used Schnorr with the Fiat-Shamir transform on, yes, I know BN256, but yeah, it was what was needed. And so yeah, this was a very slow machine also. So, but it was, let's say, in comparison to the full mixing process, because in Hyperledger Fabric, what they did is they also mix other things up, and they have it's a really nice signing process that's happening. And the auditing part was really, in comparison, very fast. So, and what I just want to let you know or show is that other wild creatures also exist in the jungle, which I, for time reasons, but yeah, didn't include that much, but which I personally liked very much, because they're very practical, very real world. So maybe that's interesting. First of all, on the right side, we had great talks yesterday and today, and we will have great talks about Zcash. Like yesterday, we had Mimblewimble and Lilantis to talk together, so yeah, you know about that. But two other things that I found while researching which I heard about, which I really liked. First, the Goldwasser and Park paper from 2018 about secret laws, where they actually design a secret law protocol using zero-knowledge proofs. And also, it's really nice to understand what problems arise when you actually do such a real-world problem, and you talk to judges, and they're like, "What is mathematics?" And it's kind of interesting. Another thing which I really, really liked was Prio. Actually, what's happening here is Prio is doing statistics using zero-knowledge proofs, which is very interesting. It's a work from Stanford. I think the people are based in Stanford, and it's a very interesting work on how to actually do that, because statistics and metrics is also a problem we have to maybe solve sooner or later, and we could try to use zero-knowledge proofs. Yeah, so this is it from my side, references, and yeah, thank you for gliding along the jungle. Thanks.